Welcome to Math341. This is lecture 22. And so what we're going to do today is we are going to do the proof of the central limit theorem in mostly full generality. Modulo some results as always from complex analysis. If time permits, and I think time will permit, we'll talk a little bit about estimating probabilities and the error function. Estimating probabilities is a very natural thing to tie into a lecture on the central limit theorem, because the whole point of the central limit theorem is to estimate probabilities. What is the probability a sample mean is sufficiently close to the true mean? And as n gets larger and larger and larger, we hope that it's going to get tighter and tighter and tighter about that. And there are more advanced theorems that will actually quantify how far away are you. These are going to use the higher moments of the distribution. You can make this a little bit more rigorous. And if I happen to know the distribution, then I can say, what n do I need to be within a certain tolerance? If you ever look at a poll, they say, we've surveyed 2,000 people, and this percent support either the cause or the candidate, and our uncertainty is plus or minus. And so, how are they able to make results like that? Well, if you make some reasonable assumptions about the population that it's drawn from, then you can actually have error bars like that. And these are extremely useful. As always, there's the power of doing simpler cases first. We did a simpler case yesterday. By yesterday, of course, I mean last class, where we looked at sums of exponential random variables. And I chose exponential because we don't have a nice form for all of the calculations we need, but it wasn't too bad. Today, unfortunately, we're not going to have as good of a result as the exponential. So what's the nicest thing we could have? Sums of Gaussians, sums of chi-squared, sums of Poisson. What are nice about the sums of all of those random variables? What kind of distributions are they? Stable. So you get the same form. It's just the moment generating function with just a different parameter. And then we just look and see what happens as the parameter goes to infinity. And you see it's converging to the moment generating function of the standard normal. And then you basically just cross your fingers, pray, and say that I can then invert and say if the moment generating functions converge, the distributions must converge. The exponential, we were able to write down a closed form expression for the sum of exponentials. It was nice. It wasn't as good, but we could still work with things. Now we're going to have to use Taylor series. And this leads to the last point, the power of logarithms. We are just used to dealing with sums rather than products. So we will take logs. So it's things that we are used to doing. All right. Since we've broken it up, yet again, at this point, this slide should be burned in your memory. The moment generating function is just the expected value of e to the tx. It does not always exist. If you take a Cauchy distribution, and I sadly had to have it truncated so it would fit in this room, you cannot get a finite moment generating function for any t other than t equals 0. So we do not always have these tools. Now, we talked about using the characteristic function, which is a close cousin. So it is the moment generating function evaluated I times t, where I is the square root of -1. And the advantage of the characteristic function is it always exists, because the absolute value of e to the I tx is just 1. So this is where some complex analysis comes in and is useful. Okay. Oops. Okay. This is another slide that, again, should be burned in memory. The reason why we call it the moment generating function is when you look at its Taylor series expansion, its coefficients are the moments divided by the factorials. If I give you a nice random variable x and I rescale it to alpha x plus beta, this is a nice linear transformation. The moment generating function transforms in a very nice way. It's e to the beta t times the moment generating function of x evaluated not at t, but now at at. And then the last is, if we want to add two random variables and look at what is the moment generating function of the sum, the moment generating function of the sum is the product of the moment generating functions. And how do you get the density for a sum? Convolution. Convolution is integration. Integration is hard, right? So if we can find ways to get around integration, that's good, right? That's essentially what we're trying to do here. We're trying to bypass difficult integration, and rather than doing an n-dimensional integral, which of course I know you can all do because you've done multivariable calculus, but if we can avoid doing that, let's go for that route. And so rather than doing the n-dimensional integral, if they're all the same, it's just raising the moment generating function to the nth power. That's much better. And then we take the limit as what's going on as n goes to infinity. If you look at where we're evaluating things, when we evaluate things at a t or alpha t, if alpha is a small number, then you're evaluating the moment generating function near 0. Well, what's the moment generating function at 0? That's just 1. So the hope is that we're going to have something that's really close to 1. And then that limit, we can then handle it without too much trouble. All right, so we've talked numerous times about standardizing random variables. This way we can only require ourselves to understand one normal distribution, the standard normal, mean 0, variance 1. So you give me any random variable, as long as it has a finite mean, I can subtract off the mean. As long as it has a finite standard deviation, I can divide by the standard deviation. So without loss of generality, it's enough to look at objects that have mean 0, variance 1. Okay. And then we talked about calculating the moment generating function of the Gaussian. We just get e to the t squared over 2. And the main idea in that was just completing the square. Okay. So then, here are the big results from complex analysis that we're assuming. Basically, high level, if the moment generating functions converge and anything you want to hold holds. Okay. So if you can prove things work for the moment generating functions, then sure, why not? We know that this is not always true. We've looked at the function e to the negative 1 over x squared, and we've seen that its Taylor series is identically 0. Taylor series are not unique. You should have been warned about this when you were younger. Your Taylor series are wonderful. I can approximate a complicated function with a simple function. That's great. And if I have a Taylor series that converges, it should converge to the original function. No, not necessarily. So this basically justifies why you take advanced analysis classes. Because dangerous things like this can happen. Most of the time it doesn't. Most of the time things are good, but it has to be proven rigorously. All right, so now it's time to calculate the moment generating function of Zn. And so please watch for algebra mistakes. All right, the earlier you find the algebra mistakes, the better. Okay, so we're going to assume x1 through xn are IID RV with mean mu and standard deviation sigma. There's lots of ways we can look at this. I'll let Zn be x1 plus xn. Now, if I want to have mean 0, what should I divide by? What should I subtract to get mean 0? So if each x has mean mu, what should I subtract to have mean 0? Not mu, because I have a sum of x1 through xn, and mu. And then the variance of the sum is the sum of the variances. So if each one has variance sigma, the variance of the sum is going to be sigma squared. The variance of the sum is going to be n times sigma squared. So the variance of that is going to be sigma square root of n. Or we could look at, x1 plus xn over n. Someone's probably trying to get in. Are you trying to get in? Hello? Hello? You trying to get in? Okay.
Yes.
Okay. Yep. Yep. Bye. Okay. And so we could look at the sample mean. And now we would divide by mu. And then I think it's divided by sigma square root of n. And that should be the equivalent thing. So again, it doesn't really matter which one I look at. Do I want to look at the sample mean or do I want to look at the sum? I can always adjust both of them. So now we can write, Zn as alpha x1 through xn plus beta, where alpha is going to be 1 over sigma square root of n, and beta is going to be negative mu over sigma, and then there's a square root of n in the numerator. Let's rewrite it so it's clear the differences between the mu's and the sigmas. Minus square root of n mu over sigma. And now we use the moment generating function of alpha x plus beta at t is e to the beta t the moment generating function of x at alpha t, and here x is just the sum of the x's. I'm not confident about my ability to go through the entire lecture without making an algebra mistake. So I'm deliberately trying to do as much as I can to minimize the chance of making an algebra mistake. Again, this is just good habits. I'm writing down what every parameter is. I'm writing down the formula I'm going to substitute into, and now I'm going to just substitute in. So again, just trying to do things to minimize the chance of making an error. So the moment generating function of Zn of t is going to be e to the beta t, which is negative square root of n mu t over sigma. And then it's going to be the moment generating function of x1 through xn evaluated at alpha t. So that's going to be t over sigma root n. And again, you have to decide how much notes do you want to take through something like this. This is one of the reasons why I always record the notes like this. So you can decide, do you want to write everything down, or do you want to just sit back and just try to follow? It is a really good conversation to have as to how do you spend your time. The more you write down, the more extensive your notes are, but the harder it is to follow what's going on. So again, there's a reason why I record things. There's a reason why. Okay, now what should we do? Well, we've got the moment generating function of a sum. They're all independent. So that's just the sum of the moment generating functions. And they're all the same. So we get the moment generating function of Zn of t is e to the negative square root of n mu t over sigma, the moment generating function of x1 at t over sigma root n to the nth power. So as you all remember very well, we were at this point on Thursday. This calculation is exactly the same as before. Up until now, we didn't use anything about the fact that it was an exponential random variable. Where did we start to use that it was an exponential random variable? By substituting in something explicitly for the moment generating function of x1. We then knew what that was, so we put it in, we raised it to the nth power, we took logs, we did algebra. Okay, unfortunately, we're now doing it in general. So I can't write down what the moment generating function is in terms of a nice closed form, but I do have a formula for the moment generating function. Right? We have this beautiful expression. I can use that. Right? Okay, so now continuing the algebra. So this is what we just proved. And then we know the moment generating function of x1 of t is going to be 1 plus the mean times t plus the second moment mu2 prime t squared over 2 factorial plus mu3 prime 3 factorial t cubed plus dot dot dot. Okay. If the mean was 0, then the second centered moment, then the second moment is the same as the variance. Right? Unfortunately, the mean is not 0. Not a big deal. This is just a small amount of bookkeeping. So we also know the variance sigma squared is equal to the expected value of x squared minus the expected value of x squared. It matters where you put the square. Well, the expected value of x squared is just the second moment, mu2 prime. The square of the expected value of x is just mu squared. So what this means is I can replace the mu2 prime with something involving mu and sigma. So we know this implies that mu2 prime is sigma squared plus mu squared. And I really hope I haven't made any algebra mistakes. Okay. So now the only thing left to do is to remember, where are we evaluating the moment generating function of x1? We're not evaluating it at t. Where do we need to evaluate it at? Alpha t. And what is alpha? 1 over sigma squared of n. So because we're evaluating it so close to 0, if you had to guess, what would be your best guess for the value of the moment generating function? Simplest answer to give me. The moment generating function of x1 at t over sigma root n is approximately So if you had to estimate it, just really quickly, if n is huge, what is the moment generating function of x1 at t over sigma root n? Not 0, 1, right? All the other terms don't really matter, right? But I take that and I raise it to the nth power. So if it's a little bit away from 1, because n is huge, it can now have an impact. Think of it as the compound interest problem. You should hopefully have seen E through continuous interest, compounding continuously. So imagine, the Bank of Miller is going to give you 2,000% interest, compounded continuously. But I will only do it for one, whatever that would be, for like 1/4,000,000th of a moment. Am I going to give you really anything? No. But if I compound it continuously and I do it, for a huge number of times, all of a sudden that little, well, that's a huge bit, that would become a tremendous amount. If I gave you just 1/4,000,000th as the interest rate, it would still become huge as I compounded more and more times. That small little bit magnifies. This is the limit as n goes to infinity of 1 plus x over n to the n equals e to the x. And so if we didn't have the exponent n, if we just had 1 plus x over n, that's about 1. But if we now compound continuously, then all of a sudden it can be magnified. And so now we look at the moment generating function of x1 at t over sigma root n, and that's going to give us 1, plus now we're going to have mu t over sigma root n. Then the next term is going to be mu2 prime, which is sigma squared plus mu squared, t squared over 2 sigma squared n. And then next is size 1 over n to the 3/2, and is it smaller or larger? And smaller terms. So the first term is going to be t over square root of n with some constants. The next term, or the t squared, if I'm putting in t over sigma root n, that's going to look like a t squared over n. The next term is going to be a t cubed. It's going to look like something over n to the 3/2. The next term is going to be something over n squared, then something over n to the 5/2, and something over n cubed. So from this point onward, you just need to show small. And you can bound that by, if things are nice, by a geometric series. You need some information about how the moments are going, but we know the moment generating function exists. So I'll talk a little bit more about that later if people are interested. Are people happy to just say, yeah, I see that as I go further and further and further, each term is going to be divided by a square root of an extra factor of square root of n. It is possible, however, that the moments are growing. But remember, the moments are fixed. And so I'm going to be getting higher and higher powers. So that's going to overwhelm. So again, we can go into as much detail about this as people want. But are people happy at a high level that the terms beyond the quadratic don't really matter? They're going to just have too high of a power of n. Now you might just say, well, maybe the quadratic and the linear terms don't matter. I mean, they're being divided by root n, and they're being divided by 2 sigma squared n. Those are going to be small. but we raise it to the nth power. And we know 1 plus x over n to the nth power is e to the x. So maybe those small terms could actually matter. By looking at the definition of e to the x, we know that if you add something of size 1 over n to 1 and raise it to the nth power, that's going to be magnified. That's going to now give you, if it's x over n, that's going to give you e to the x. So I expect up to here can matter. Right? We saw that by looking at e to the x. In fact, I'm a little terrified by the fact that we have a square root of n in the denominator. That's much larger than the x over root n. If you wanted to, imagine you have 1 plus, x root n over n to the n, and just pretend that's going to be e to the x root n. I've got to be careful about doing something like this. But that should hopefully show you that, oh God, if I have something of size root n, maybe it's going to blow up. So are people a little bit afraid that if I raise this to the nth power, it might blow up? We've got something of size 1 over square root of n. That's just too big. What's going to prevent it from blowing up? What saves the day? So the moment generating function of x1 to the nth power, that could blow up because of the 1 over square root of n. Is there anything that might help us? Do we have a factor that might prevent it from blowing up? Yeah, it's the e term right before. Is we have this factor here. And notice they both have a mu t over sigma. So the mu t over sigma is going to be the same sign, but one of them has a minus sign versus the other one has a plus sign. So they're going to be of opposite sign. So the hope is that that piece is going to counterbalance the other piece. Okay, so now we need to keep doing algebra. Hopefully it's still saved. Yes, it's still saved. And we know, I'm lazy. And I'll just copy this over to the other side as well. So now we're going to substitute things in. And we're going to first take a logarithm, because the log is going to convert the products to sums, and we're just more comfortable with that. And I will just record the log of 1 plus u is u minus u squared over 2 plus u cubed over 3 minus u to the 4th over 4 plus ... So you should know that Taylor series expansion. Okay. If you don't know that, try to prove it. If you have trouble, talk to me, talk to the TAs. And we've talked before about why this is reasonable. If u is small and positive, 1 plus u is a little bit greater than 1. It's starting off with a plus u, that's great. If u is negative, 1 plus u is a little bit less than 1. Its logarithm should be negative, great. All right, so now let's take logarithms. So we get the log of the moment generating function of Zn of t is the log. Okay, so I'm going to just do some of the algebra at once. The log of a product is the sum of the logs. The log of the first piece, the log of the exponential of something, is just whatever that something is. So we start off with a minus square root of n mu t over sigma. Now we have the log of the moment generating function of x1 to the nth power, or we can just pull out the nth power, and it's then going to be n times the log of the moment generating function, evaluated at t over sigma root n. So I just put things in. So it's going to be 1 plus mu t over sigma root n plus sigma squared plus mu squared t squared over 2 sigma squared n plus ... Okay. Now we need to start doing some more algebra. Unfortunately, things are a little bit involved for us. What is u? This whole thing here is our u. So when I want to use the Taylor series expansion for the log of 1 plus u, u has a linear term, it has a quadratic term, it has a cubic term, etc. And again, this is where you have to roll up your sleeves and do a little bit more algebra. The higher order terms don't really matter. The cubic term is not going to matter when I start expanding things. And so as I start doing the algebra, I see that this is going to be negative square root of n mu t over sigma plus n. And now I have u. All right, what's u? U is going to be mu t over sigma square root of n plus sigma squared plus mu squared t squared over 2 sigma squared n plus dot dot dot. Now I have to subtract off 1/2 u squared, right? So I have 1/2, and then again, it's good to be the king. You know what movie that is from? I'll just copy what u is, and I'll just put that here. And now I have to square it. And then I keep going. Okay. Now, when I look at the dot, dot, dot at the end, all of those are going to be at least, cubing u. The main term of u is of size 1 over square root of n. So when I cube it, it's going to be of size 1 over n to the 3/2. I'm multiplying by an n outside. N times 1 over n to the 3/2 is 1 over n to the half. It's going to be small. And again, this is where you just carefully go through and keep track of all the errors. But because n is going to infinity, I have to be a little bit careful. But once I have a term of size 1 over n to the 3/2, that's going to be so small that even when I multiply it by n, it's going to be insignificant. Now, for the terms of size 1 over n, if I multiply by n, it's going to be significant. And for a term of size 1 over square root of n, when I multiply it by n, it's going to be even worse. It's going to be of size square root of n. It's be going off to infinity. All right. Is anybody excited about squaring u and looking at all the cross terms? No. Do we need to worry about squaring? Can I just say screw the square? I'm sorry? What do you mean by goes to infinity?
I get that the later terms don't matter.
The later terms don't matter. But when I'm looking at this piece right here, whoa, when I did that, I lost the 2? How did that happen? All right, I'll do it this way. No, wait. All right, there we go. When I do it this way, okay. I have to square that. When I square it, how many terms do I get? Technically infinitely many. I can forget about the dot, dot, dot when I square, because all of those are going to have at least a 1 over n to the 3/2. So those don't really matter. So if I forget about those, I'm left with the linear and the quadratic term. I square it, I'm going to get 3 terms. But when I get 3 terms, look at what happens. This term is going to give me something of size 1 over n when I square, when it hits itself. When these two hit, that's going to be giving me something of 1 over n to the 3/2. And then, haven't used purple yet today. When I have this hit itself, it's going to be of size 1 over n squared. So really, when I'm looking at what happens when I square that second term, the dot, dot, dot doesn't matter. And of the 3 terms, the only term that's going to survive is when the linear term hits itself. That's going to give me a 1 over n. And everything else is going to give me something of size 1 over n to the 3/2. If you wanted to keep track of the rate of convergence, then we would have to keep track of all this stuff. And then you could talk about how quickly does the central limit theorem set in. I know you're all begging me to keep track at that level and write down something explicitly. It could be done though. It's not that hard. It's just algebra. Should you be doing this algebra by hand? No, feed this into a symbolic program and have it expand. Right? This is the 21st century. Right? All right, so now we just have to keep expanding things. All right, so let's move on. And so we are getting close. And so what we're going to do is we are going to just drop everything here except for the square of the first term. And so when we square the first term, it's going to give us a mu squared t squared, and then the denominator is going to become a sigma squared n plus dot 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 times n. Okay? And this is, of course, the log of the moment generating function. So I'll just put that back over here. So the log of the moment generating function of Zn of t. All right, well, now let's just start multiplying things out. Root n mu t over sigma. Now the n hits the first term. We have an n divided by square root of n. That's going to be a square root of n upstairs, mu t over sigma. Oh, they perfectly balance and cancel. So this is a wonderful technique that happens all the time. You see this often in physics, where you have things going to infinity, but they're going to, one is going maybe to infinity, one's going to negative infinity, and they're going at the same rate so that they cancel, and you're left with something that's finite. And so at every moment, we have something that's well behaved. And in the limit, it's going to be well behaved. Those will be fine. Now we have n hits everything else. So now we have sigma squared plus mu squared t squared. The n's cancel, divided by 2 sigma squared, minus 1/2 mu squared t squared over sigma squared plus dot dot dot. Okay. No, there is not. Because we had an n in the denominator and we're multiplying by n. Notice how well we live, right? The first two pieces cancel, and the second one, we have a mu squared t squared over 2 sigma squared. We have a mu squared t squared over 2 sigma squared. One has a plus sign, one has a minus sign. Those cancel. And we're just left with the log of the moment generating function of Zn of t is equal to sigma squared t squared over 2 plus dot dot dot. I'm sorry, there's a sigma squared down here. So this is just equal to t squared over 2 plus dot dot dot. So the moment generating function of Zn of t, if we exponentiate, is just e to the t squared over 2 times e to the something of size 1 over square root of n. So if we take the limit as n goes to infinity of the moment generating function of Zn of t, that's going to just be e to the t squared over 2. And amazingly, we actually did this without an algebra mistake. If you compare this to what we did with the exponential, it's more work. Where is the main work? The main work is basically showing that we can ignore the dot dot dots. It was really nice to have the moment generating function of the exponential being explicit. And then we could just do the calculations directly. But it's really not that much harder. And so now we know that the moment generating function is converging to the moment generating function of the Gaussian. And now this is where you tap your heels together 3 times and hope that this implies that you can invert. Do people at least know the reference? Okay. The best description I ever heard from that movie is a young girl travels to a strange psychedelic landscape and kills the first person she meets, then teams up with 3 complete strangers to kill again. What movie is that?
Kansas, oh God.
Wizard of Oz.
Yes.
It's a nice way of describing the Wizard of Oz. We've now proven the central limit theorem, modulo some results from complex analysis. So if people are interested, you can email me. I'm happy to give you a quick crash course in complex analysis, either individually or in one of the classes that we have remaining. This is not going to be on exams. Yeah, the rest of the stuff after today is going to be more on applications. So we actually don't need this slide. I gave myself too much space. Can anybody figure out what's going on these slides? What do you think the blue curve is? Nope. You should recognize the blue curve. You should have known it in high school before you, not sine, okay. Cosine. All right, the blue curve is cosine. What do you think the first yellow curve is, gold curve is, the second one, the third one, the fourth one? What do you think those are? They're the Taylor series approximations. So cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. So if I just do a 0th or a first order Taylor series, it's going to just be a horizontal line. If I do a second or a third Taylor order series, it's going to be the parabola 1 minus x squared over 2 factorial. The whole point of this is to show you how quickly the Taylor series converges. If I'm looking at n equals 6, I've almost got it from minus pi to pi. That's not bad. Just going up to a polynomial of degree 6, I've almost got cosine between minus pi and pi. If I go a little bit further, here's 24 and 28. It's incredible how many cycles it does. To some extent, I don't really need to have it go through that many cycles. I can always assume that x is between minus pi and pi. But it's incredible how quickly this converges. Why do I have this? Well, you want to ask that question about the sample mean. We know the sample mean is converging to the Gaussian. We want to know how quickly, we want to know what can we say about that. So there's a whole advanced topic about stuff like that. But it's just worth getting a sense of how quickly convergence is happening. All right, so what if I want to calculate the probability that the absolute value of x is greater than n if x is, say, a standard normal? So I chose the absolute value of x so that we can have at least 2 ways of estimating that probability with things you've seen already this semester. We have Markov. So by Markov, the probability that the absolute value of x is greater than n is less than or equal to the expected value of the absolute value of x divided by n. Okay, so the expected value of x, of the absolute value of x, well, if I just had x, what would be the expected value of x? For a standard normal, what would be the expected value of x? 0. It would just be 0. So this would be the integral from minus infinity to infinity, the absolute value of x, 1 over square root of 2 pi, e to the negative x squared over 2 dx. This is just going to be twice the integral from 0 to infinity of 1 over square root of 2 pi, e to the negative x squared over 2 x dx. I'm choosing to put the x there because I remember how to do this integral. All right. Why is e to the minus x squared over 2 difficult to integrate? Because the exponent has an x squared. We don't want to have a dx associated with that. We want to have an x dx. So let's just put the x next to it. And so now, if we let u equal x squared over 2, then du is going to be x dx. And if x goes from 0 to infinity, u is going to go from 0 to infinity. And so the expected value is just going to be 2 over the square root of 2 pi, integral u goes from 0 to infinity, e to the minus u du. Oh, that's not a bad integral to do. What does that integral equal? Taking too long. 1. Why does it equal 1? I'm sorry? It's a probability distribution, right? You've got to be able to recognize certain things immediately. This is an exponential random variable with parameter 1. It has to integrate to 1. So I know the answer is just 2 over the square root of 2 pi. So Markov gives the probability is less than or equal to 2 over square root of 2 pi. That's the same as square root of 2 over pi divided by n. So Markov is telling us it's decaying like 1 over n. What about Chebyshev? The probability that the absolute value of x is greater than n. Can we write this in a good way for Chebyshev? I could write this as, as x minus 0 greater than or equal to n times 1. That my distance from the mean is at least n standard deviations away. So what does Chebyshev tell us? So if you're n standard deviation, if your case, I think we used the letter k before. If you were k standard deviations away, Chebyshev says you're at most what? 1 over k squared. So this gives us that that probability is at most 1 over n squared. So this gives you a little bit of a sense of how much better Chebyshev is doing than Markov. You know, we're using more information, we're getting something a little bit better. And I just had to be slightly clever to write this in a way so I could use Chebyshev. You know, Chebyshev is being, you know, some number of standard deviations away from the mean. So I write, so the cleverness is I write the absolute value of x as the absolute value of x minus the mean. And since the mean is 0, you know, these are really all the same. Okay, so if I take n equals 10, the probability that you're 10 standard deviations away is at most 1%. If I take n equals 1, you know, the probability is at most 100%. Okay, that's kind of useless. If I take n equals 2, then it says, you know, for a standard normal variable, the probability that you're at least, you know, 2 standard deviations, that you're at least 2 standard deviations away is at most 25%. Do we think that these are reasonable? Well, if you look at the bell curve as to how quickly it's decaying, these are terrible bounds for large n. And so the question is, can we do a little bit better? So we want to calculate, you know, the probability the absolute value of x is greater than n. This is going to be twice the integral x goes from n to infinity, e to the negative x squared over 2 dx. Oh, and we have a 1 over square root of 2 pi. Okay. So does everyone agree that this is the calculation we need to do? Yes? So we want to estimate this probability. So there's a lot of ways to do this. Has anybody here taken real analysis? I will. Right. So you may be, so if you've taken real analysis, you know you've made it if your name becomes a verb. So you can think about using the Cauchy-Schwarz inequality to do some things later on. So one thing we can do is we can say, look, we'll assume n is greater than or equal to 1, e to the negative x squared over 2. I can replace that with e to the negative x over 2. That's going to be an upper bound. You know, x is going to be at least n. This is going to be an upper bound because x squared is going to be a lot larger than x. And so our integral will be less than or equal to the square root of 2 over pi. The integral x goes from n to infinity, e to the negative x over 2. And now, e to the negative x over 2, I would want to have a 2 over here and a 2 over here to cancel that so things will be nice. And when I integrate that, I'm going to get an e to the negative n over 2 from one bound, and I'm going to get 0 from the other. And so if I've done all the algebra correctly, this should come out to like 2 root 2 over square root of pi e to the negative n halves. So that's one way to try to estimate what the probability is. That's much better than a 1 over n or 1 over n squared. We now have something that's exponentially decaying. Let's do something else. Let's write x as n plus t. So x goes from n to infinity, has t go from 0 to infinity. And so x squared is going to be n squared plus 2nt plus t squared. So the probability that the absolute value of x is greater than or equal to n is going to be the square root of 2 over pi, the integral t goes from 0 to infinity, e to the negative n squared plus 2nt plus t squared over 2 dt. The advantage of that is I can pull out e to the negative n squared over 2. And so I'm going to get the square root of 2 over pi, e to the negative n squared over 2. And now I have the integral t goes from 0 to infinity, e to the negative, the 2's cancel, nt. And then I have e to the negative t squared over 2 dt. And this is where, if you've seen the Cauchy-Schwarz inequality, you could actually use Cauchy-Schwarz here, where these are your two functions. So you could use Cauchy-Schwarz if you are familiar with what that is. Both of those functions are at most 1. So if I drop one of them, I'm only going to get an upper bound. E to the minus t squared over 2, well, when t is close to 0, that's not so bad. I can actually get some savings by looking at e to the negative nt. Right, that's going to give me another exponential. Does anybody know what the integral of e to the minus nt would be? Not quite. So this is going to be less than equal to square root of 2 over pi, e to the negative n squared over 2, integral t goes from 0 to infinity, e to the minus nt dt. Okay. I've just dropped e to the minus t squared over 2. Well, if you think about this, e to the minus nt looks a lot like an exponential random variable. Let's get parameter n. So I should multiply by an n here and divide by an n over here. And now that's going to integrate to 1. Right? And so this should give me, if I've done the algebra correctly, square root of 2 over pi, e to the negative n squared over 2 divided by n. So I'm just showing off a little bit by getting the extra factor of n in the denominator. Doesn't really matter. I've already got an e to the minus n squared over 2. You know, that has tremendous decay. But now if you put in something like n equals 10, you know, if we just used Chebyshev, Chebyshev says the probability that you're at least 10 standard deviations away for the standard normal is at most 1%. It's correct, but how close is it to the truth? This is not the truth. I think you could handle the truth, but this is not the truth. This is an upper bound on the truth. And if I put in, okay, maybe you can't, it phased out. If you put in n equals 10, you get e to the negative 50. Right? E to the negative 50 is terrible. As an aside, you know, if I want to get just a really bad bound for e to the negative 50, do we agree that's less than 2 to the negative 50? And 2 to the negative 50 is 2 to the 10 to the negative 5. 2 to the 10 is 10 cubed. So this is 10 to the negative 15. So just as a really bad estimate, because E is more than 2. But as a quick estimate, ballpark, it's at most 1 over 10 to the 15, much less than 1%. So just because Chebyshev is true doesn't mean it's giving you anything close to the truth. It's just giving you an upper bound that has to be true. We really want to calculate probabilities well. And so we need to find ways to calculate areas under curves. We don't need that space. So the only curve, what's the only normal we need to care about? Standard normal. Does this function over here, does this look like the standard normal? I'm not asking, is it the standard normal? I'm saying, does it look like the standard normal? Yeah, it's got a square root of pi. It's got an exponential of a negative variable squared. It's looking good. But what should the exponent be if it's going to be a standard normal? Over 2 sigma squared. We just have an e to the negative t squared. So if you were to guess, what kind of normal does this look like? Looks like a normal with variance equal to what? One half. Because you were supposed to have e to the negative, say, t squared over 2 sigma squared. And so it's looking like it's a normal with variance 1/2. Joy, right? After all of the conversations about how, without loss of generality, we just have to look at the standard normal, the error function is defined not with the standard normal, but with the normal with variance 1/2. It all comes down to which is going to lead to the best algebra, and just you have to be a little bit careful going back and forth. If you've taken math and physics classes, you will have noticed at times they have slightly different notation. The physicists like to have theta as the variable coming down in spherical from the z-axis, whereas the mathematicians like to have phi. I learned it first from the physicists, so I always have to fight when I'm teaching multivariable calculus here to use the mathematician's notation. Does it matter if I call it theta or phi? No. But it's very easy to get mixed up because the two are not the same. So over here for the error function is defined in terms of almost the standard normal, but not quite. Slight shift. Why is this useful? Well, let's say I want to calculate what is the probability that x, which is say normal 0, 1, is at most little x. That would be the integral from -infinity to x, 1 over square root of 2 pi, e to the negative t squared over 2 dt. This is using the cumulative distribution function, right? What's the probability I take on a value at most x? I just integrate from -infinity to x. All right. Does anybody know a closed form expression for the integral of e to the negative t squared? Is there a nice function whose derivative is e to the negative t squared over 2? No, we don't have a closed form expression. So we need some way to approximate this integral. Does anybody know a good expansion for the exponential? What does e to the u equal? This is one of the ones you need to know. This has to be hardwired at this point. What is the series expansion for e to the u? The sum n goes from 0 to infinity of u to the n over n factorial. This is something you just have to know. You may be embarrassed or afraid to say this out loud, but you got to know the expansion for e to the u. Does this converge for all values of u? Yeah, the factorial grows so rapidly that the growth of u to the n is much slower than the growth of n factorial for fixed u. So we have the integral from minus infinity to x, 1 over square root of 2 pi, the sum, n goes from 0 to infinity, of u to the n over n factorial. Oh, but u is equal to t squared over 2, right? So t squared over 2 to the n dt, which is the integral from minus infinity to x. I'll pull out the square root of 2 pi. We have a sum, n goes from 0 to infinity. We have a t to the 2n. And not only do we have an n factorial now, but we also have a 2 to the n in the denominator. So what should we do now? So we have an integral of a sum. What should we do? Switch them, right? You've learned two things in multivariable calculus when you went to the integration section. Change variables, switch orders of integration. Can I switch the order of integration? Oh, sorry. I dropped the negative sign. So we'll have -1 to the n. Am I allowed to switch the orders of integration? The series does converge for all values. Am I allowed to just switch the orders? So how many of you remember Fubini's theorem? So in multivariable calculus, you should have seen you can switch the orders of integration if the double integral of the absolute value is finite. We're going to see there's some problems. I will put a question mark here. Can we switch? That would give us 1 over square root of 2 pi. The sum, n goes from 0 to infinity, -1 to the n over n factorial 2 to the n, integral from minus infinity to x of t to the 2n dt. All right, well, what's the integral of t to the 2n? So what do I get if I integrate t to the 2n? I don't want to cold call people. What do I get if I integrate t cubed? What function is derivative t cubed? Somebody who hasn't spoken in a while. What's the integral of t cubed? Somebody who hasn't spoken. I'm going to start cold calling people. So what function? Yes. Good, t to the 4th over 4. So somebody else who hasn't spoken in a while. What's the integral of t to the 8th? So what function has derivative t to the 8th? 1/9 t to the 9. So if I'm integrating t to the 2n, it's just going to be t to the 2n plus 1 over 2n plus 1. And I evaluated minus infinity and x. Right? When I put in the minus infinity, I'm going to now have an alternating series of plus and minus infinities. So this cannot justify. The issue is the integral of the sum of the absolute values is infinite. That's the problem. So even though the exponential series expansion converges for all u, I can't just put that in and switch the integral and the sum. I think it's extremely important for you to be aware of the dangers. So for instance, I did not do all the algebra for the central limit theorem. I could easily do the algebra and show that the dot, dot, dot terms don't matter. It was already a lot of writing. Hopefully it was enough that you could see, I've got square roots of n, it's not going to really make a huge difference. Here's an example where you might just start working naively, but unfortunately there's a problem. And so at first, this looks like we're in trouble. Is there any value of little x where you know what the probability of a normal 0, 1 random variable is to be at most x? Any value of x you know.
0.
Good. If x equals 0, what's the probability? The probability is 1/2. So we know that. So here is the brilliant idea. The probability that x is less than or equal to little x is the probability x is less than or equal to 0 plus the probability, let's say x 0 less than or equal to x less than or equal to little x. If x is greater than or equal to 0, and it's minus the probability of x less than or equal to big X less than or equal to 0 if x is less than or equal to 0. So if x equals 0, we haven't gone far enough. So we basically know here is 0, and the probability up to here is 1/2. And so if I choose my x over here, I just have to add a little bit to that probability. If I choose my x over here, I just have to subtract a little bit from the probability. I went too far. So what we're doing, in some sense, this is really similar to like a lot of Taylor series expansions. You take a point where you know things, and then you expand around your knowledge. So this goes back to one of your goals for today. In some sense, this is very similar to the Taylor series. I know what's going on at the origin, and I know my instantaneous speed, and I know my instantaneous acceleration. I can use that to approximate what's going on in a small window. And if it's a sufficiently small window, it's pretty good. If I try to do the whole calculation from minus infinity, good luck. I have this alternating sums of infinities. Earlier today, we did two. We did two terms that were going to infinity, but they were never actually infinity, right? It was for finite value of n, we had two finite numbers. They were both going to, one was going to plus infinity, one was going to minus infinity at exactly the same rate, and they could cancel each other out. What we just had a moment ago was completely different. We just had an alternating series of sums of infinities. So here what we do is we just know that if we go up to 0, it's 1/2. And then we just have to do the correction from that point onward. So for example, if x is greater than or equal to 0, the probability 0 less than or equal to my random variable x less than or equal to little x is going to be the integral from 0 to x of 1 over the square root of 2 pi e to the negative t squared over 2 dt. And now we can do the same game we were doing a moment ago. It's 1 over the square root of 2 pi, integral 0 to x, the sum, n goes from 0 to infinity, e to the negative t squared over 2, oh, I'm sorry. I'm not doing the series expansion. So it's going to be negative 1 to the n, t to the 2n over n factorial 2 to the n dt. This is going to be 1 over square root of 2 pi. The sum, n goes from 0 to infinity, negative 1 to the n over n factorial 2 to the n, integral from 0 to x, t to the 2n dt. And this can now be justified because the n factorial 2 to the n, that has such great decay down below that the integral is not going to be a problem. And so now, what do we get? We're going to get a t to the 2n plus 1 over 2n plus 1. So when x equals 0, that's always going to be 0 because it's going to be at least t to the first power. So this is going to just be 1 over square root of 2 pi, the sum, n goes from 0 to infinity, negative 1 to the n, x to the 2n plus 1 over n factorial 2 to the n, 2n plus 1 if I've done things correctly. And that would be the probability. So we can actually write down a series expansion for the probability of getting a value between 0 and x. If I wanted to be between minus x and x, just double this. If I wanted to be the probability that most x and x is negative, I would subtract this. If I wanted to be the probability that it's at most x and x is greater than 0, I would add a half to this. It's all these simple games. And so now if you go back a few slides, here we have this error function. The error function is going to be related to a series expansion of this, except instead of using the standard normal, they use the normal with variance 1/2. All right. So you are allowed to like things or not like things. That doesn't mean you have the freedom not to use it, but you can say, do you like it or not? Something related to this is the error function. It's some kind of infinite series expansion like this. What do you think? Nice or not nice? So I see you're shaking your head. So why is this not nice? Why isn't this a nice function? Give me examples of nice functions. Well, I want examples. Give me a nice function. Log. So we'll allow log. Okay, so you'll start with log. So that's your first example when I ask for a nice function. You went straight to log. Sine, cosine. All right. Wow. Okay. Sine x, cosine x. What? Yeah, x to the n, polynomials. Right. So maybe we'll have the list going in reverse order like this. My son's, car needed gas. And so, the car looks like this. This is the front, this is the back, and it listed the tires. And this is the spare. If you label the tires 1, 2, 3, 4, it took me a while because I had to pump up each tire one at a time and then figure out where things were going. This is how it displayed things. I would never choose to display it like that. That's how they chose to do it. I'll read this from bottom up. We start off with the nicest thing, polynomials, and then you have sines and cosines, you have the trig functions, and then you have the logarithm. Well, if you're going to have the logarithm, what else should you have with the logarithm? Yeah, I mean, you got to keep you got to have the exponential there as well if you're going to have the logarithm. So does everybody agree sine and cosine are nice functions? We are allowed to discriminate amongst functions. Okay, it's not a protected category. Okay, functions can be, you can say this, you can say you're not a good function. First thing I did when I got tenure is I asked, is being a Yankee fan a protected category? I was told no. I've never taken any penalties to anybody who is a Yankee fan, but it's not a protected category. Do you consider polynomials nice functions? Yeah, I don't think anybody's going to argue that a polynomial is an ugly function. Why do you think sine and cosine are nice functions? Okay, so they're periodic. That's nice. That's a nice property. Okay, so if I give you, say, f of x is, 1 minus 2x plus, let's say 8x squared, what's f of 1/2? It's 1 minus 2 times 1/2 plus 8 times 1/4. 2, 3, is it 2? Yes? Oh, sorry, 3. Sorry, 3. Yes, sorry. It's 2. Yeah, it's 2. It's 2. It's 2. It's kind of sad that we're having this much trouble calculating. But do we agree that it's not that bad to evaluate a polynomial?
Yes.
All right. What's cosine of 1/2? Cosine of 1/2 is, yes. I'm waiting. It's 1 minus 1/2 squared over 2 factorial plus 1/2 to the 4th over 4 factorial minus 1/2 to the 6th over 6 factorial. Yeah, I don't know a nice closed form expression for what that is. But you consider sine and cosine nice functions. Why? We gave them a name. And they have nice properties. You know, the derivative of sine is cosine, the derivative of cosine is minus sine. We just gave them a name and you're willing to consider them a nice function now. Yes?
When you like use forget like fractions of pi, they're like very easy values.
Certain values of certain fractions of pi. I can do anything by playing some games, yes, if it's a fraction of pi. But if I want to evaluate cosine at 1/2, that's not a big ask. And so it's worth spending some time philosophically and thinking about what you consider nice, how you've been brainwashed. Right? Everybody, I think, agrees that sine and cosine are nice functions. We are used to them. We are experienced with them. They're old friends or old enemies, depending on how you feel about your high school math classes. We've known them for a long period of time. And you think they're nice. They have a name. The name error function, I mean, that's not the greatest name possible. It's almost like you're deliberately trying to make people not like the function. But if I can give anything a name, and then the question is, how hard is it to work with? Well, the error function does have a series expansion. It's going to be close to the series expansion at the bottom of this page. It's a little bit different because it's a normal with variance 1/2, not variance 1. I didn't want to play those games, but it's not a big deal. We can write a series expansion for the error function, and it's related to the probability under the associated normal distribution from 0 to x. It's not going to have as nice of an interplay as sine goes to cosine when we take the derivative, cosine goes to sine. We're not going to have stuff like that. But just because we've given something a name doesn't mean it's nice. Sine and cosine do have a lot of nice properties. There's geometric definitions of them. There's relations, angle addition formulas, stuff like that. There's a lot of wonderful things. It's the same thing for the exponential function. It's the same thing for the logarithm. How would you calculate the log of certain things? Now, the derivative of the log is the 1/over function, which is nice. If I try to take the derivative of the series expansion, actually, the derivative isn't so bad, right? The derivative will just essentially give me like an e to the minus t squared over 2. Things will cancel nicely. So it really is worth thinking about what do you consider nice, what do you consider a mess. We can give anything a name. And as if the name is used enough times, you just get used to it and you start to think it's nice. But there really is a lot of work behind doing any calculations with sines and cosines. So this is a good place to stop. Again, for the rest of the semester, I really don't want to do much new material. I think you're going to have a lot of new material in other classes you're taking as they wrap up. I want to spend the rest of the time doing applications. So on Thursday, we will do the method of least squares and linear regression. You may have seen this in other classes, but it's good to see it from different perspectives.